So you've learned how to make Lewis dot diagrams. Now it's time to understand why we did that in the first place. What are covalent bonds? And let's connect them back to the Lewis dot diagrams. By the end of this video, you should be able to recall all the Lewis dot diagram information from before and now apply it to the facets you learn about covalent bonding. We'll start with a warm-up of making some molecules using Lewis dot diagrams and single, double, or triple bonds. Then we'll figure out what the heck these covalent bonds are to begin with and the two flavors of polar and nonpolar. And then we'll talk about some diatomics and summarize at the end with a graphic organizer that you could print out and put in your notebook if you so choose. And here's our warm-up, ladies and gentlemen. If we are going to draw a Lewis dot diagram for CO2, we need to notice that there's one carbon atom and two oxygen atoms. We'll draw a C and two O's. I'm kind of skipping steps here. I'm already putting the more electronegative atom, that is C, in the middle between the two O's. Now I need to draw the valence electrons around each atom respectively. Carbon has 4 valence, 1, 2, 3, 4, and I got that from looking at the periodic table. And oxygen has a valence of 6. So 1, 2, 3, 4, 5, 6. I'm going to make the other oxygen atom look the exact same. Now all we have to do is pair up those lonely electrons. We've got a lonely one there, and there, there, and there. We're going to clean up this molecule, make it look a lot nicer before you turn it into your chemistry teacher. Draw C, 2 lines, O, 2 lines, O. Don't forget to bring over these lone pairs on each oxygen. And then that would be our final answer for CO2. How about CH2O? We have 1 C, 2 H's, 1 O. Let's start by drawing our least electronegative atom in the middle, just so we can skip a few steps. C, 2 H's, we know H's are normally on the outside, and an O. We need to draw in the valence electrons for each atom respectively. Hydrogen has 1 valence electron, so we'll just draw 1 next to each. Carbon has 4. Again, I'm gathering this from the periodic table. If you don't have these memorized as of yet, look at your periodic table to determine the valence number. Oxygen, we have 6. 1, 2, 3, 4, 5, and 6. Now time to just pair up all those lonely electrons together. We'll put an H there, another H there. This carbon can go there and there. Of course, we need to clean up this molecule. So we'll have a C. We have a single bond to each H, a single line, and we have 2 lines going to oxygen. Don't forget to bring those lone pairs up on the oxygen as well. And there you have it, CH2O. Our last warm-up is PCl5. Remember that P is one of the exceptions. Phosphorus has the exception of expanded valence. So we can break up a pair of electrons on phosphorus, and it's totally cool with that. So we have 1 P, and we have 5 Cl atoms. We're going to just draw these Cl atoms all around. There we go. Now we need to draw in our valence electrons for each atom respectively. Phosphorus has 5 valence electrons. 1, 2, 3, 4, 5. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Where did I get those numbers? The periodic table. You need to look. We're going to make the other chlorines look the same. Now let's connect those lonely dots together. We've got a lonely one here, we've got a lonely one there, and we've got a lonely one there. Uh-oh, we have a pair here that we would normally not break apart, but in this case we have to. Phosphorus is the exception. We can break those apart. So we're going to break up the happy couple so that one can bond with this chlorine and the other can bond with that chlorine. That looks like a horrible mess. Let's clean it up. We've got P in the middle, and all single bonds to each chlorine. Cl, 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 Cl. Don't forget to bring down all of these lone pairs on each chlorine atom. I know it's tedious, but it is required. You need to show those every time. And that would be our final answer. As a challenge, I implore you to try and determine the polarity and IMFs of each of these molecules. I'll give you an example for the first one. If we're going to look at polarity, we're going to draw from the least electronegative atom to the most, how the electrons are going to go or where they want to be. So for CO2, we would draw an arrow from carbon to oxygen with a little plus on the butt, and also from carbon to oxygen with a little plus on the butt. If you're thinking about these like vectors in physics, you would notice that both of these vectors are of equal magnitude pointing in opposite directions, therefore they cancel out and our polarity would be non-polar for a CO2 molecule. Okay, so then what about the intermolecular forces, the IMFs? We have various intermolecular forces, London dispersion, which is also known as van der Waals. There are hydrogen bonds, there's ion dipole, and there's also dip-dip or dipole-dipole. Those are your intermolecular forces. So if we had another molecule of CO2 right next to it, how would they interact with each other? Because that would be between molecules, intermolecular. There's no hydrogen present, so it couldn't be hydrogen bonds. We know that van der Waals or London dispersion forces are usually between long chains of carbon. That's not really what we're seeing here, so it couldn't be that either. Dipole-dipole is when you have a dipole. In other words, you have an area that is slightly positive and slightly negative. That'll kind of attract to each other that way. And then there's ion dipole. Well, we don't have any ions here because we don't have a full negative charge anywhere. So the only option that we have for CO2 in our intermolecular forces is dipole-dipole. Go ahead and give the polarity and IMFs a try for CH2 and PCl5. So in the warm-up, I mentioned IMFs, intermolecular forces. Those are between two separate molecules. We're now going to delve into a molecule and talk about the chemical bonds. So a chemical bond is considered an intramolecular bond. It is something inside the molecule itself, holding the atoms together. Chemical bonds can be holding atoms that are different or the same together. If they are the same atoms, we call it an element. If they are different atoms, we call it a compound. So from the picture I've showed here, the two same colored atoms at the top would be symbolizing an element, and the orange and the blue atoms would be symbolizing a compound. Those two circles held together by a chemical bond, both of which, as a flashback, elements and compounds are both molecules. Keep in mind and keep them differentiated that a chemical bond is within a molecule and an intermolecular force is outside of a molecule, between two different ones. So for example, a chemical bond would be the fact that your arm is physically attached to your body. That's the bond to your body. However, if you were to push on another person with your arm to their body, that would be like an intermolecular force. In chemistry, there are three kinds of bonds that we talk about. That's covalent, ionic, and metallic. However, we're starting off with covalent, and that's all we will be talking about for right now. A covalent bond is composed of non-metal atoms only, and these non-metal atoms are sharing electrons between them. They share in order to have a full valence shell. So the non-metal atoms are sharing only their valence electrons between each other. And the sharing is so that they can both have a full octet and complete the octet rule, making them all happy and kind of pretending like they are noble gases. There are two flavors of covalent bonds. One is polar or unequal sharing, and the second is nonpolar or equal sharing of electrons. So think of it like you trying to share your automobile with your best friend or maybe a sibling. Perhaps your parents got you both a vehicle to share. There's likely not a chance that you're both sharing that vehicle equally. Likely your sibling or your friend is kind of hogging your vehicle, and that would be an unequal sharing. Yeah, you still get to drive the car, but you don't necessarily have the car the majority of the time. That would be like a polar bond, for example, an unequal sharing of said object of electrons for these atoms. Please keep in mind the most important thing here is that covalent bonds will only ever occur between non-metal atoms. They do not happen between a metal and a non-metal. They don't happen between metal atoms. It is always non-metal atoms. How do you know what are non-metal atoms? You have to look at your periodic table and discern which side has only the non-metal atoms present. If those are the only thing present in the molecule, then it's covalently bonded. Let me pose a question to you. If electrons were to be pulled towards the more electronegative atom, and you have two different non-metal atoms, like say O and H, is this an equal or unequal pull? Hopefully you should know that oxygen is a heck of a lot more electronegative than hydrogen is. Therefore, this is an unequal pole. In other words, oxygen gets that vehicle, that car, gets to drive it around a lot more than hydrogen does. And because of this, we call it a polar covalent molecule. It is covalently bonded because there are nonmetal atoms present. They are different nonmetal atoms, so that would make it a compound. A compound that's a molecule that happens to be polar because they're not sharing the electrons equally. On the flip side, if there were electrons being pulled toward the more electronegative atom and you have two of the same or different nonmetal atoms connected together, is this equal or unequal pole? Well, in this case, even if there's two different ones, but they're being pulled towards the same amount of strength, if you will, this would be an equal pole. This would be like having a tug of war with yourself. You're not going anywhere. You've matched each other's strengths, so to speak. So this is a nonpolar covalent molecule. The electrons are being shared equally between all of the atoms present. So let me see if you actually understand what's going on here. Between these options 1 through 5, which of these molecules are covalently bonded? Remember what I said before. What type of atoms must they be? If we look at our periodic table that way, we can see that anything in blue is a metal, anything that's orange is a metalloid, and metalloids do count as nonmetals in this scenario, and anything that's green is a nonmetal. So what we're looking for are molecules or compounds that are composed only of nonmetal atoms. So if we look at number 1, that's NaCl. Well, if we find Na on the periodic table, it is blue. It's a metal. It can't be a covalent bond because there's a metal atom present. Even though Cl is a nonmetal, it's in the green section of the periodic table, it's bonded to something that's a metal. That means it cannot be covalently bonded. It breaks our definition. Number 2, H2O. We have two H's. Well, H is green, so check mark. And oxygen is also green, check mark. Both of those are nonmetals. Therefore, water, H2O, is a covalently bonded compound molecule. Number 3, aluminum chloride, AlCl3. Aluminium, hopefully you know off the top of your head, is something that you use in your kitchen for cooking and things like that. It's a metal. So it's in that blue region all the way in column 13. Since that's blue, since it's a metal, and our definition for a covalent bond means they all have to be nonmetal atoms, number 3 cannot be a covalent bond. How about number 4? SeO. Se you can find in the 16th column right below oxygen and sulfur, and since it is in that green region of being a nonmetal on the periodic table, and so is oxygen, this would be a covalently bonded compound molecule. And last but not least, number 5, we have N2. N is in our green region, nonmetal. There's 2 of them. Yes, that would be a covalently bonded element. Not a compound because it's 2 of the same atoms. So here's the extra challenge for you. Are those bonds for the covalently bonded molecules polar or nonpolar? For number 2, for water, we see that there's something that's really electronegative, oxygen, connected to hydrogen, which is not. That one would be polar. Moving on to number 4, we have Se and O. Since oxygen is closer to fluorine when we think about our periodic table trend going up across and towards fluorine being the most electronegative, we could hypothesize that oxygen would hoard those electrons a little bit more tightly than Se would. Because of this, it would be polar. Number 5, we have 2 of the same atoms covalently bonded together. That means that N is essentially playing tug of war with itself, like you and your clone playing tug of war. You're not going to be hoarding electrons one over the other. Your strengths are matched out to each other. So in this case, N2 would be nonpolar. Now that you know what a covalently bonded molecule looks like and what it's composed of, only nonmetal atoms, what are these things called diatomics? Let's break down the word. Di means 2, atomic means atom. So 2 atoms that happen to be the same. These exist naturally and they can never be alone. If they do happen to be alone, they end up hooking up with themselves. So diatomics, there are 7 of them. that will literally never be an atom just by itself. You'll always see at least a little 2 denoted next to them because they can't be alone. Hydrogen is one of these examples. Hydrogen H2, you would never just see an H because hydrogen is a diatomic molecule. It will always find itself if it happens to be alone. So for example, hydrogen gas exists as H2, HH. In other words, there's never just going to be an H present because H needs to have a full octet. It needs to feel full, having 2 electrons. So it's always going to find another H atom that it can share and have 2 electrons with. Aww. Here are the 7 total diatomic elements, molecules, that you should know. It's probably a good idea to outline them on your periodic table, and if you do so, it conveniently makes a 7, and there are 7 of them total. Here they all are in case you can't really read it from the picture. H2 is hydrogen, N2 nitrogen, O2 oxygen, F2 fluorine, Br2 bromine, Cl2 chlorine, and I2 iodine. So if you wanted to outline your diatomics, this is how you do so. You want to outline your hydrogen as one of your diatomics just to remind yourself that this would always come in H2. You would never see it just as H. We also have, starting from nitrogen, all the way down to iodine, just like that. Conveniently makes a little 7. All of those are going to be paired together if they happen to be alone. Now, this is a topic I saw a lot of confusion with when I taught in high school. So let me clarify here for a minute. If someone were to say hydrogen fluoride, that literally means HF. H is already bonded to F. So you wouldn't write it as H2F just because, oh, hydrogen's diatomic. That means there has to be 2 of them, right? No, that's not the case. H already has a buddy. H already has fluorine. I told you it's hydrogen fluoride. So hydrogen already has fluoride as its buddy. However, if I would just say hydrogen, then you would write H2. You wouldn't just write H by itself. In this case, I said hydrogen, so you would have to know, oh, hydrogen can't be alone. It's not just going to be H, it's going to be H2. Again, if I said hydrogen chloride, hydrogen fluoride, hydrogen anything, you would never just have 2 H's connected with whatever it is I told you just because it's diatomic. You only apply the diatomic rule if all I say is hydrogen or nitrogen or oxygen or fluorine or chlorine or bromine or iodine. So here's the whole thing in a nutshell. Covalent bonds form between multiple non-metal atoms only, and they share electrons. Why do they share electrons? They share them in order to have a full valence shell and octet. There are also 2 flavors of covalent bonding. There's polar, which is an unequal sharing of electrons between 2 non-metal atoms, and there's nonpolar, which would be an equal sharing of electrons between 2 non-metal atoms. If you're not much of a word person, here's a graphic organizer. So starting from the top box, are all the atoms connected together non-metal atoms? If you're given a molecule of something, are all the atoms present only non-metal atoms? Yes, then it's a covalent bond. No, then it could be ionic or metallic. More on this later. Let's continue with the yes. If it happens to be a covalent bond, do the vectors and or the bond angles cancel out? So go back to the polarity lesson if you don't know what I'm talking about here, between all the non-metal atoms present. If they do cancel out, yes, that would be a nonpolar covalent bond. However, if they don't all cancel out, you end up having a vector or an area of a lot of electronegativity, so no, then that would be a polar covalent bond. Let's move on to the nonpolar. If in the nonpolar covalent bond, they all happen to be the same exact type of atom, all N2, all H2, all O2, Cl2, F2, etc., then that would be a diatomic molecule. I hope this helps you understand covalent bonds a little bit better. And let's all act like covalent bonds in this new year 2021. Let's share kindness, guys. Seriously. Start the new year off right and be a covalent bond. Give me a thumbs up on the video and subscribe if you haven't already. See you later.
No ducks, no glory.